circular shaft. So if this is a z-axis, then that's the direction of the torque, right? The arrow is just, the arrow shows the direction clockwise, counterclockwise, but really the direction of the torque is where your thumb points when you curl your fingers along that arrow. So take a right hand, curl it along the direction of that arrow, and your thumb gives the direction of the torque. Okay, so let's think of a small cross section. Okay, I'm going to blow this up. Okay, this thing is at a distance of rho. That's the radius of some circular cross section of the circular shaft. Okay, so let's say that we just draw a line from the center to a point on the circumference of that circle of radius rho. And then we twist it, we apply a twisting moment. The moment we put a twist, you will see that this OC will move along the theta direction or the circumferential direction and move to a new position C prime. That's what torsion will do. It will twist the shaft, right? So let's say that, so this is the end of the shaft. This angle is, let's call it gamma. And then this is the length of the shaft. So now this is based purely on geometry. C prime is the arc length. If I assume that this angle is theta, then CC prime is the radius times theta. Right? That's the definition of arc length. But I can compute the arc length another way. I can use the angle of twist, gamma, times L to compute that. So gamma times L is also the arc length. So what I have effectively is I can compute the angle of twist, rho theta divided by L. Okay, if you want to find the maximum twist, then you do what you do is you put rho equals C, which is the radius. L. So gamma is angle of this is theta is the angle of twist. This is the shear strain. Theta is angle of twist. Rho C is radius. And rho is also radius. But rho is the radius of some circular section, and C is the maximum value of rho. Okay, now by definition, so let me just circle that. That's an important formula. Now by definition, the bulk modulus G is the ratio of tau divided by shear strain. Bulk. And this is very similar to a definition for normal Young's modulus. Young's modulus is defined as the normal stress, sigma, divided by the strain. In this case, this is the shear analog of that, tau, which is the shear stress divided by shear strain. So tau equals G gamma. And then some people like to write a formula for G gamma in terms of rho. So we can write this as G rho theta divided by, I just substituted the value for shear strain. That's our formula number 2. L in the bottom, yeah. Okay, and then the maximum shear stress can be obtained by putting rho equals C, which is the radius of the shaft. Tau max equals G C theta divided by L. And so this is how the shear stress will look. So if you draw a circular cross section, this is the center, and then you would understand how the shear stress changes as the radius increases. Then it's basically 0 at the center, and it goes to a maximum on the outer edge. So this is tau max, and then this is tau, right? So tau divided by tau max. You can take those two formulas I circled, and you can see that it is simply rho divided by C. So the shear stress varies linearly with distance from the center. Okay, one last thing and I'll let you go. If you have a circular hollow shaft, say something like this, then the stress will look something like this. This will be tau max. This will be tau min. It's not equal to 0 because of the way the shaft is. And then tau divided by say tau min divided by tau max will be, let's say C0 is the C1 is the inner diameter, and C outer is the outer diameter, then it'll just be the ratio of these two. So again, it will be linear. Okay, so I'm going to consider a small area on the cross section of area, say dA, and the shear stress is at right angles to the radius, rho. So we know that the formula for torque is, well, it's a moment, right? So it's force. That's the force, which is, in this case, it's the shear force times moment arm. But the shear force is nothing but torque times T, right? That's the definition of shear force. It's the shear stress times the area over which it acts. And since this is over an elemental area, I need to take the integral over the entire area. But we know that we derived this formula, tau divided by tau max equals rho divided by C. In other words, the shear stress is the max stress rho divided by C. And so I can sub that in here. max. So there's another row there, so rho square divided by c, where c is the radius. Again, I can extract tau max and see. I'm left with this. So rho square times dA, the integral over the entire area, is also known as the polar moment of inertia. Again, the symbol used is J. And so we have another expression for the, well, we have an expression for torque. So torque is tau max J divided by the radius. Let's see, is radius of cylinder or shaft. So let me usually, you know what, may not put it this way. Usually what you are given is torque is given and you need to find tau max. So we as well write the formula for tau max. It's Tc divided by J. So that's a better way of writing and remembering the formula. Torque. It should be the same one we used for inertias, A18. Usually the most important ones are torsion of cylindrical sections. And so the reason why it's important is because when you have a non-circular section and you twist it, you see that plane sections don't remain plane and they sort of protrude out of the plane of the paper. And so when you typically design machine elements, you do not go for a non-circular section when something is subject to torsion. You typically limit it to circular cross sections. So that's what you want to use. The JG for the solid cylinder and JG for the hollow cylinder, which is just have to use the superposition and subtract out d raised to 4, which is the inner diameter. Okay, so summary. It looks like there are too many formulas, but there are really very few formulas here. I'll just try to write the minimum set of formulas I possibly can. So gamma equals rho theta divided by L. Okay, rho is the shear strain over a radius rho, but if you want to find the maximum, you'll obviously put rho equals C, which is the maximum radius of the radius of the shaft. That's the second one is derived from the first one, so it's not a new formula. Okay, tau is T rho divided by J, and tau max is T C divided by J. And there's one more formula. The angle of twist is T L divided by J times G. And that's all to it. So really, there are 3 unique formulas. The ones in the first column.
Does the rho stand for the radius?
Yes, rho is, let me just draw it here. If you have a circle, so I'm drawing a side view, so it looks like an ellipse. Okay, this is not a hollow shaft. I'm just drawing another radius. That's the shaft. The axis. This is the torque. This is rho, and C is the max of it. Okay, then the stress, and this is something which you'll see later is very important. That is, you need to know how the shear stress is actually acting. And if you don't get it here, then it just becomes harder later on. So the shear stress would be, the maximum shear stress would be like this. So it's pointing this way and not the other way because of the direction of torque. The torque is counterclockwise, so the shear stress will be counterclockwise. So what will happen is there will be a maximum shear stress, like so. And you can see that all the arrows are counterclockwise because the torque is counterclockwise. Similarly, there will be a smaller stress on that inner circle of diameter rho, and I'll call that, this will be tau. So you see the difference. Tau is the stress, shear stress on radius rho, and tau max is the shear stress at the radius c. Okay.
What are the arrows that are inside of the inner radius?
You
Like,
mean,
are those both, oh no, that's just regular tau, right?
you mean the,
Yeah, it's I see what you mean. I just, like the arrows on the inner radius is tau, and then the radius on the outer is tau.
right, tau max. The other way people like to show this is a circle, tau max, that's tau, and obviously it's 0, so you can draw a straight line because it's linear. Here's the first problem. So the shaft shown has an inner and outer diameters of 4" and 6". Respectively, the maximum allowable shear stress is 12 KSI. Find the maximum torque that can be transmitted by the shaft without failing. So the outer diameter is 6". Inner is 4". This is 12. Okay, so let's identify what formula will help us to compute torque. Okay, we just look here. So tau max is given, the radiuses are given, so it should be this one, right, where we put tau equals tau max. So tau max equals T C divided by J. And now the question is, what C would you use? Well, the maximum stress occurs where the C is maximum. And so we'll go for outer diameter. Now, maybe I should write this here. So this D0 is the diameter. So that should be twice the radius and twice the inner radius. Okay, so tau max is known. Torque is unknown. C0 is known, it's 3. We need to compute J. Okay, so for J, we go to that appendix, which I showed you, A18, pluck out the value for J for a hollow cylinder. And yeah. Yeah, because C is radius, T is diameter, and so the diameter is twice the radius. Yeah, so from table A18, we have J equals pi. It's T raised to 4 divided by 32. But then this has 2 diameters, so it should be T raised to 4 minus T raised to 4. Right. Six raised to 4 minus 4 raised to 4 comes out to be 102.1 inch raised to 4. And so tau max is 12 ksi, so 12 times 10 raised to 3 equals T. C0 is half of 6, so 6 divided by 2. J is 102.1. So when you do this, you'll get the answer in, well, I would just get the answer in Kippage. So let's not substitute KSI, just keep it as, substitute the value for K in the KSI. So just put 12. In that way, the answer for torque will be in Kippage, right? So this would give me T equals 408.4 kip inch. So shaft AB and CD are solid of diameter D. Right here, the colors. Well, clearly D is not given. While shaft BC is hollow of inner and outer diameters of 90 and 120 mm. What it's saying is that this shaft here between B and C is actually hollow. Between BC. There is 2 diameters. Outer diameter is 120. And the inner diameter is 90 mm. Okay, the shaft assembly is subject to torques as shown. There are a bunch of torques at A, B, C, and D. Okay, we need to plot the torque as a function of shaft length, minimum shearing stress in shaft BC, and the diameter D if the allowable shearing stress is 65 MPa. So tau max 65 MPa. Okay, so the book doesn't quite emphasize torque diagrams, torque as a function of length, but I think they're important because unless you find the torque as a function of length, you don't know where the torque would be maximum. And if you don't know where the torque is maximum, you cannot compute where the shear stress is maximum. So you sort of not be able to design something unless you know the maximum. So we're going to try to draw the torque as a function of distance. So torque as a function of the shaft length. And then, this is something there's no real sign convention here in the book. So we just come up with our own sign convention. So you can start either from left and go right, or from right to left. Now, this particular shaft with this loading is not supported anywhere. Okay, this is actually already the free body diagram is already given to you. But if it was supported by whatever pin joints or roller joints, you have to first draw the free body diagram, compute the reaction torques, then you'll get a diagram which looks like this, and then you can draw the torque shaft length diagram, which I'm about to draw. Okay, so this is the free body diagram, apparently. Okay, so what we'll do is we can use the same analysis method we used for computing the shear force in a beam. We just cut the shaft at different points where the torque has already changed. So the torque is, for example, if the torque is applied at A, we can cut it anywhere from A and B to figure out what the torque is between A and B. So let's just do that. So let me draw the diagram on the left and do the math on the right, or the free body diagram on the right. So from A to B, just draw it in the same view. So at A, we have a torque of 6. Okay, and that's counterclockwise. And what we'll do is there's a torque which is needed, which is the reaction torque now, because we cut the shaft at somewhere between A and B. And so that torque resists the 6 kilonewton meter torque. Okay, now we can choose any sign convention you want. If you want to choose clockwise as positive, counterclockwise positive, you can do that. So plus 6, that torque is counterclockwise, minus T equals 0, which is saying that the torque is 6. Okay. Let me just draw it, say here, 6. So it is 6, it will be 6 for the entire length till B. Okay, then I draw the same figure for the section between B and C. So I again need to go all the way from A to somewhere between B and C. So there is 6 counterclockwise, there's 14 counterclockwise, and then this is going to be our reaction torque. Okay, so 6 plus 6 plus 14 minus T equals 0, which means T equals 20. So the torque now increases between B and C. So B to C is 0.9 meters. So then the torque has increased, should be somewhere there, 20. Okay, then between C and D, we have to make a cut and then do the same thing. Write the equations of equilibrium, the shaft. Let me write these values here, be easier when you refer to it. So that's A, this is A, this is B. So let's put A, B, C, and then show the torques there. 6, 14. At C, there is a clockwise torque of 26, and then that's the unknown. So 6 positive, 14 positive, 26 negative, torque T negative gives me I think -6. Yeah. So we go with 24.7 meters. Then the torque will decrease to -6. So it'll remain -6 till you reach this point T, where you have a counterclockwise torque. So that -6 adds to the 6 and you get 0. So this, by the way, is also starts at 0. That because beyond D to the right, there's no torque. So it should add up to 0. And to the left of A, there's no torque. So it should also add up to 0. So it's important that there's a 0 on the extremes. Okay, so that's the torque as a function of length. Next, let's solve for the maximum shear stress. Okay, now you're told that the maximum shear stress in shaft BC, there is no question about, if D was given to you, then maybe a good question would be find, compute the maximum stress, in which case what you have to do is you have to figure out where the maximum torque occurs and then figure out what the maximum stress is. Now, here's the catch, which is just because the torque is maximum at between B and C, I should put it down here, A, B, C, and D. Just because the torque is maximum at between B and C doesn't mean that the shear stress is maximum at B and C. That's because if you look at the formula for maximum stress, it's T R or TC divided by J. Okay, so you would think that it's maximum when T is maximum, but that's not true because it also depends on J and C. So you have to do that computation to figure out what C and J is and then put it there to figure out where the maximum shear stress is. So just don't assume that maximum M means maximum, maximum T means maximum shear stress. It could be somewhere else. And that only happens because here the diameter, it's hollow in some places and it's not hollow in other places. If it was uniform, then yeah, you're good with starting with 20 Newton meter is where the kilonewton meter is where the maximum shear stress will occur. Anyway, so here we asked to find the maximum minimum shear stress in shaft BC. This is BC, it's hollow. So let's first write the formula and then compute the value. Okay, so we know that the way that the maximum stress will occur is it will be max on the outer circle, and the minimum on the inner circle. Right? It should be linear like this. That's tau max, that's tau min. Okay, so what's the formula? We need to use this formula. Torque equals T rho divided by J. So tau max is T C outer divided by J, and tau minimum is T C inner divided by J. So T is, in this case, the T is the torque at the shaft BC, which from the previous figure, we saw it was 20 kilonewton meter. C outer is 120, it's 120 mm diameter. So it's 60 mm. C inner is half of 90, 45 mm. The J is, so again, you go to table A18 and plug the value for J for a hollow cylinder. It's pi divided by 32 dO raised to 4 minus D inner raised to 4. If you want in terms of radius, it's D is twice C0, twice C inner. So that comes out to be pi divided by 2 C0 raised to 4, Ci raised to 4. And so we know what the values of those things are. C0 is 60 mm, which is 0.06 raised to 4. Minus 0.045 raised to 4. So I get J equals 13.9 times 10 raised to negative 6 raised to 4. Okay, and then using these formulas, tau max equals 86.2 MPa. Tau min is 64.7.
How do you go from pi over 32 to pi over 2?
It's because of this 2IC. Okay. So it turns out we've done most of the work for last part, which is figuring out the diameter. So last, let's go. Okay. The diameter D, if the allowable shearing stress in shaft AB and CD is 65 MPa. So we need to compute D and D. Well, if you look at the stresses between A and B, it's 6 and it's 6. Right? So it's the same magnitude, different sign. Okay, which means that if the shear stress between AB is clockwise, then in CD it will be counterclockwise or vice versa, depending on the sign, the correct way it is set up. So you could use AB to design it or CD to design. It doesn't really matter. Now, if the question was if the stresses were the torques were different, AB had a different torque than CD, then there's a design problem, right? You need to figure out which shaft has maximum torque and use that to design the diameter. Okay, but here it's kind of straightforward. So let's use either of them. So we'll use 6 as our torque, and then we'll use whatever value they've given for maximum shear stress. This problem is last part is similar to what we've done the previous. The previous problem is similar to the previous problem where we were asked to solve for maximum. Well, in that case, we were not asked to solve for diameter, but here we asked for diameter. So the formula is the same, T times C outer divided by J for shaft AB or CD. So tau max is given is 65 times 10 raised to 6. The torque is 6 kilonewton meter. In this case, it's really, well, I shouldn't have put C0, it's just C. There's no inner and outer, it's a hollow solid shaft, not a hollow shaft. So that's C. And then by using table A18, we get the value for the, what do you call the J. That's pi divided by 32 d raised to 4, but I want to convert that to radius. So I put d equals to c. Five, 10 raised to 6, 6 times 10 raised to 3. This will give me pi divided by 2. And then the C4, the C and this 4 cancels, giving me C. No, that's not right. That's C cubed. So C is 6 times 10 raised to 3 divided by times 65. Cube root of that. So C, after solving this, you get C equals 38.9. But you're asked to find the diameter. So the diameter is twice C, which is 77.8. So that's the final answer. This part is on torsion of non-circular sections. In fact, we'll do rectangular sections. Torsion of rectangular shafts. Okay, so the thing about the difference is that when we've talked about circular shafts, previous section, plane faces cross sections remain plane when subject to torque. Okay, but with rectangular sections, that's not true. Plane sections do not remain plane. So they get distorted. Okay, so an example, this is kind of hard to draw, but let me try. So if you have a shaft, which is rectangular, and you twist it or torque it. If you have a sponge, you can try, which is cut into a rectangular, you'll see that when you twist it, or rather I put, see, this edge will go like so. This is the inner edge. It's so hard to draw. So this is hard to draw because this actually is not plane anymore. It actually comes out of the plane. So if you torque something which is circular, then all sections will be in the same plane. If you torque something which is rectangular, then it will come out of plane. That's really hard to show here. It goes out of plane. Okay, so how do we? So there's a way you can compute what's the maximum torque, maximum shear stress for a given torque and maximum angle of twist. And that derivation is beyond this book. In fact, if you do a higher level course in solid mechanics, they might teach you how to derive that expression. So I'm just going to give you an empirical formula, and that's what we'll use for this. So the derivation for tau max and theta is beyond scope. And so what we do is we pretty much use a table to compute those two things. So I just have to write the formulas, what's B and what's alpha. So we use this. Okay, so the formulas are tau max equals T divided by alpha times BC cube, and theta equals T times L divided by beta B C cube divided by G. And what's B and C? That's the last part, and I'm done for that. B and C are the dimensions like so. So C is this. This is B. And this is L. And the assumption is that the torque is applied on this axis. Okay, so if you're given that torque, even given the dimensions, alpha, beta comes from that table, B divided by C, the ratio is given there, and how to choose alpha and beta. That's the formula we'll use.